Okay, good morning. Today I am going to talk, this lecture is termed as Imo Requirements. International Maritime Organization, they have now some requirements regarding maneuvering standards. I will talk about that mainly. But before I go to this, I want to complete what we left yesterday, that is hill during turn, because that part we couldn't complete. This is basically a set of rules regarding the zigzag and turning maneuvers, but let us talk about the hill during turn before that. Okay. So, we are looking at ship turning this side, So, I had a cross section yesterday drawn. Let me use color pen. So, this is the G here, and we had here this force, because it is turning this side, that is mass into V square by R. Okay, m is the mass. This is everybody knows. In fact, V by R is omega, so it's m V omega whatever equal to, you can say m V small r. Small r is V by R. Okay. Okay. Now we have also here rudder force that comes here. This is my rudder. Okay. Typically rudder will be of this type. So rudder force come here acting F rudder, which will turn out to be equal to y delta r into delta r. This is the y force that comes. Essentially that is what you say by definition. And as the ship is turning, obviously it is going to produce a reaction force which is Fh. Okay, maybe it is acting at a point, we call it E here, this is H here, this point, this is G here, this is keel here. Fh is equal to, in a steady turn, is YVV plus YRR. Basically Fh is the Y force on the hull, and the hull Y force is actually because of dy by dv v and dy by dr r, because it has got only v and r, it does not have v dot and r dot right now. Okay. In the case of initial phase, you will have v dot and r dot. I will come to that afterwards. This is on the, I am looking at hill during turn, which is steady turn. Now we have to look at this here. Now you see, according to our mathematics, F H minus F R, there is a net force on this side should equal to force on this side. This should be equal to m v square by r. Okay. And the moment, this is the force equation, the net force is 0, and the moment equation I will tell you. Now we want to find out what is the moment causing hill, the net moment causing hill. So if we look at about, say, moment about G, is Fh minus Fr into Kg. We actually, I am just following this here. H is this one minus Fh to Ke. This will turn out to be, I will simply write the final result. Ge. See what we have done. See, it's very simple here. We are taking moment about this point. What is the moment about this point? It is Fh into Ge, this distance. The heeling moment. See, we are talking of heeling moment in this direction. Okay. Fh into Ge minus Fr into Gh. Okay. This we are writing in this form simply for some other reason. Actually, that one only we broke down because that will turn out to be equal to FH minus FR into FH minus FR into GE minus FR into EH. The reason we are want to write it is because we wanted to write in terms of FH minus FR. This formula is extremely simple. I have got a force and acting at point 1, another force acting at point 2 and taking moment about this point. And we find out that the moment is absolutely straightforward. The main reason of writing this is that it turns out for many ships EH is very small. Why? Because you see rudder will be typically over the entire draft, mostly, slightly less than the draft. So, it will come about middle of that. As you can see, the rudder is not really ending at this point or ending at this point. Normally, you try to make a rudder which is, because you want to take more area, so you increase that rudder up to more or less waterline, design waterline. And this part will also come at more or less center of that. So, therefore, FH and FR are more or less collinear. One can always try to find out where is the center of action, but it turns out for all ships this is very similar, so that this is almost 0. This is why it is written this way, EH, because they will act more or less in the same line. So that my moment turns out to be like this. This is the reason of writing that. Okay. So once we know the moment causing this heel, obviously we can find out the amount of heel, which we will just talk. So this should be understood. So this becomes the moment causing heel, FH minus FR, and you can actually find out what is FH minus FR. As I said, FH is YVV plus YRR and FR is Y delta L delta R. So if you know the hydrodynamic derivatives, we can find out. Now obviously delta, or we can see delta GM, in fact I should say weight here, mass into G, I want to rather write this way, the GM sin phi, phi is a heeling angle, this we have done it before, is equal to heeling moment. This is FH minus FR into GE, which is equal to, now if you look back that FH minus FR, oh actually there is one more way of looking at that, FH minus FR without going to this is equal to mv square by R. FH minus FR is mv square by R. So if I put that, it is even more simpler, it is mv square by R into G. Okay. So we can get this m out, then it will turn out that R into G into sin phi, okay, by V square equal to G by GA. So from there you can find out phi, or rather, in fact we could have done it from here only, V square GE, V square G by R GM into GM, like that. So you see you can find out this more or less, and GE, what is E? If you look at that, E can be taken more or less to be half the draft. Yeah, if this is a draft here, you can take half of the draft, T by 2. See, we are looking at KE to be T by 2. We'll work out some, we can work out some problem later on. So like that we can easily find out. So this, now of course from there you can easily find out phi. If phi, we have written it sin phi, but if phi is small, we can always say that phi equal to so much. Okay, that's very simple. This is how we actually find out. Let us say that we will be, let us do a kind of problem, okay, a typical numerical problem, where R is say 300 meter. I am just looking at a typical number that might come. Say some ship is turning at 300 meter, because it turns out that R by L lies between 3 to 4 for most ships. Okay, for more, in fact, we will talk about Imo requirement where it says that it should be less than 5. So R by L is about 3 to 4. So let us say this is a small ship, say 100 meter long ship, so 300 meter R. Okay.
The radius of turning is the length of the ship.
Radius of turning normally for a large ship, it should be about, it normally lies between 3 to 4 or around 4, you can say. But for a navy ships, very tight turning, that double rudder ship can be as small as even 2. It can turn. Radius is 2, that means diameter is 4. Remember that. In fact, if you see this diagram of simulation, the ship scale is like that, it will look something like that, at some turn. I mean, I am just showing an instantaneous diagram. If the ship is a scale diagram, if ship length is so much, okay, there are cases where within this, within this almost R, almost 1.5 type, you can have pictures of ship turning like this, just to give a feel. Anyhow, if we have got this R equal to this thing, V equal to say 20 knot. Of course, you can make out the interesting thing that obviously, if the ship is shallow and high, the G is above, very much high. Of course, G is very much high, GM also tends to be low. Then and this ship has a larger draft, then this becomes more. This increases. If this increases, then there is a increase in the angle. If speed is increases, increase in the angle, or R reduces, increase in the angle. This angle, therefore, the ship will more heal if it make a tight turn. This ship will turn more than if there is a larger one, obviously, because the centrifugal force is more. GM, again you can make out it is inversely proportional to GM. As GM is high, angle is low, etc., etc. GM is high, obviously the stiffness is more, so you need more moment to heal. So if you do that, and the draft of the ship, this is draft, say 5 meter, and kg is say 6 meter, and GM equal to. Okay, here actually it is, see, draft is for this ship, draft is 5 meter. So you can take the center of action to be halfway through, and kg is 6 meter, that is, k to g is 6 meter. So I can take this to be 2.5 meter, so that this distance becomes 3.5 meter. So you see what happened, GE becomes approximately 3.5 meter. Okay. Actually, I let me do it in a different piece of paper. It's getting small. See, we have got this ship now here, which says the draft is 5 meter. This is K. This is G. Kg is 6 meter. Okay. V is 20 knots. To say, 10 into something, 10 into 0.5144, sorry, 20 meter by second. Okay.
Kg we are taking as 6 meters, sir.
Kg is 6 meter, and GM is given as 2 meter. So what I mean is that you can take point E to be halfway to this draft, so you can take this to be 2.5 meter. And therefore, this is 3.5. Therefore, if I go back to this formula, V square G by RGM, see sin phi, V square G by RGM, this will turn out to be, you can see the units also, this is unitless, V square is meter by second, so it is, let me write this to be approximately 10.28 or something, okay, 10.288 square into G is 3.5. This is, let me see the check, the meter square by second square into meter, okay, this is the unit. R is 300, that is meter here. G is 9.8 meter by second square, GM is another meter 2. Okay, so you see this all matching. This will turn out to be some number. So here from there it will turn out that phi is approximately 3.5 degree. You can work it, it is of this order, okay, you can just work it out.
So G comes to this thing.
Difference now.
With
So we
G.
are taking it as center, sir. E we are taking as center.
Yeah.
Center of the draft.
We are taking it halfway to the draft. See, I mean, this engineering approximation, okay, where will it be, tell me? Where will when there is a flat.
H and FR is at that point.
Yeah, but you tell me logically, there is a pressure acting here throughout this. Where is the expected center? Will it be somewhere very much on the top, or will it be somewhere here? It will be somewhere in this region, halfway through. Rudder is always more or less on the draft. Where will be the center of pressure? It will be always, if not center, I tell you, it will be within plus minus 10%. So you don't go too much wrong, you see. Okay, you don't like 2.5 meter, you make it 2.25 meter. You will get probably little more, maybe 3.8 degree. So it will be of that order. You are making an engineering judgment, I mean, when nothing is there, you have to use your kind of judgment on that. So you can get this. That's what I am trying to say. One interesting point that is to be said about this, you see. Suppose the ship is turning. Now you see here, which side the ship is turning? It is, as it turns here, it is heeling on this side, outward. So you will see this picture of the ship heeling like that as it turns. I got a nice picture on my desk of an aircraft carrier turning this side where it is heeling. You can make out that the heel is, in fact, it is as much as 10 degree or so, you can make out. Next time you come, I show you. I have got that on my table. Very nice picture. You cannot make a mistake of the turn because the wake will tell you which side it turns, the aerial picture. The interesting point there that I want to mention, two things. One is that, see, supposing suddenly you decide to stop this rudder. So the ship is turning, you decide to stop the rudder. What will happen? Tell me in this equation. What will happen? Now you see this force is Fh minus Fr. Okay, that is a force. If you look at that, I will just put it in this way, then it will be easier. See here, I have got Fh minus Fr into G is this formula. Okay, because this is Fh minus Fr. Now suddenly I want to reduce Fr. If I make Fr 0, because suddenly if I turn my rudder angle to 0, Fr is after all y dr delta. So suddenly I make delta at 0. So this will go to 0. So this will go to 0, but at the same time the speed V and R will not come to 0 because the ship is V and R is moving. So this will still remain as much, almost as much, but this will suddenly go to 0. See, you are going to bring the rudder back to 0 in say 5 seconds. Normally 3 or 4 degree per second is there, say like that. But velocity has not come down, as you know, ship, you know much more than me that it will take long time. So suddenly you are reducing this to 0. What happened? Earlier it was Fh minus Fr G, now it is Fhg. Which one is more? This is much more. So suddenly it is going to find much more of turning moment. That is why if you suddenly stop, it will have a jolt and try to heel more. It may in fact heel more and may capsize. This is why it is suggested that you should not bring the rudder down back to 0 when it is making a sharp turn. During the turn, very quickly, you should do it very slowly so that you know that there is an adjustment time. In fact, an interesting point is that this I want to tell you also that initial phase, if you remember the first phase of the turn, as soon as you put the rudder up, okay, this reaction force is actually small. Okay, reaction force is small. So you have given a rudder force but no reaction force. So at that time the ship turning inward. So initial phases the ship turns inward and then the reaction force becomes the acceleration force. If you recall, you will find out that the reaction force was yv dot v dot because we had first phase only v dot and r dot, no v and r. So initially when you put the rudder, I immediately have this force, but no, not this force. What happened? The ship has actually turned inside. So it initially, as soon as you put rudder, ship turns this side, then it begins to turn this side. Okay. And that is why this all, and also you can see from the magnitude the typical turn will look something like this. This is what another diagram I show it to you, that as it turns, if this is the turn angle, phi angle here, let us say finally it will turn here. First phase no turn is there. This is a plus minus whatever. First phase it will actually have 0, then it turns this side initially, then it has outside this side, then actually it comes down and comes down. Why? I will tell you why it is like this. Now there is also interesting point. Initially at this phase you have no angle. Why initially it has turned inward? This is inward and this is inward turn. This is inward angle that is turning on this side angle, because I don't have Fr but I have Fa. I have Fr but no Fh. So therefore it turns this side. So initially it turns this side. So maximum turn, then eventually this side begins to come up. So it is going to reduce and begin to turn on the other side. Then there is a point when this Fh is large because it has got both V dot and R dot as well as V and R. This is where it is more. That is in a transient phase. My total force is yv dot V dot plus yr dot R dot plus yv plus yrr. So it is more. Then eventually the acceleration force reduces, so it comes down and comes down like that.
So Fh will always dominate.
Huh?
Fh will always be higher than Fh.
Yeah. Yeah, FH will be always ultimately higher than that, and it will always turn this way. Yes, that you are right. FH is all, because that there is also a reason for that. See, FH is a reaction acting on the entire hull. If you look at the hull, it is on this entire hull, and this is only on this part. So you know this entire force is acting on that. So it is always so. But this is interesting how that in here no force, in here FR dominates, in here FH, but this FH is larger than the actual FH, and here also of course FH. Here FH due to V dot R dot, here only due to V and R. So you see, this is now at this point suddenly if you reduce that, it is going to actually snap roll, what they call snap roll actually. It can certainly have a large roll. Okay, so it's just an interesting part of rolling along with during maneuver. This is of course obvious that as you turn.
This would be also explained on the basis of that initially you don't have any centrifugal force.
Yeah. Actually, the centrifugal force, actually, when you say that, it's a question of chicken and egg problem, which comes first. Actually, this is like an inertia force which is always existing when there is a V. V will come because of this force. So, you can see that way. It's only equivalence, but it's like mass into acceleration is force. But you have to give force to get acceleration. So this is like that acceleration part. So first you give FR, that is why there is a V setup, that is why this comes, and this part actually is only in the steady turning time. So when you don't think of a steady turning time, you don't know what force when dot and all coming, you can think there is a force coming here, but take that point to be the point of action and take moment about that, so that action force does not contribute.
It is only FH will be.
Yeah, FH and FR, and of course the relative magnitude of that.
So when rudder is brought to zero in the moment of turning, so FH will try to heal it other way.
Yes, because if you are suddenly, initially you have no FH, only FR, so it is turning this side inward. Then eventually FH becomes more, so it like this diagram we showed. Yeah, it is turning on. Say it is turning.
Same rudder position.
Yeah, same rudder position. Rudder is already finished here. Okay, so you have given a rudder. Say you want to make a port turn or starboard turn. Okay. So you have given a rudder accordingly, on this side. The question of convention, like you have given a rudder on this side, so the ship will turn. So initially the ship will first heel in the starboard side, say little bit, maybe 3 degree. Then it will now begin to go on the other side, may go to 5 degree, and then eventually come little less and then stabilize. So it will first start like that. So it will go first of all, it will shift this side, no? So it will shift this side with this angle. Difficult to say, shift this side, this angle. Then it is going to go like that, and then slowly like this and turn. And then if you suddenly touch this thing, it will go more. So this is an interesting point to see, that. So therefore, it is the same thing that when you are turning, you should not suddenly change. And I tell you one interesting thing. It is said that many of these small boats that plies in river, like vessel, they capsize not only because of low GM, also for this reason. Sometimes they turn very heavily and suddenly change, and they don't know there is a snap roll there. You see, yeah, river ferries and all. So this also is a reason. It is not something to be neglected. That maneuvering is a reason, because it tends to. All you need is for 1 second GM to become negative, then capsize. You don't need for a long time, just for an instant the GM should become negative, or it should have a large angle, so it will capsize. Anyhow, now we'll come to this Imo requirement. I wanted to speak this today. Obviously, it is on maneuver. See, IMO has given, in fact, this some clause, I think A751, and it has now changed to, I don't remember, MSC 76. These are all clauses, forget it, but they have got some resolution. It reads long thing. I am not going to write down the rules and regulation. All step does not make sense. That you can read, and best would be the project on a screen. But I wanted to tell about only some essential features of that. You see, that nowadays what happened for all ships, in order to assess that it has got some kind of directional stability and some kind of turning ability, IMO stipulates some requirements saying that it must maintain these. I will just basically broadly mention those requirements. First of all, the standards they tell apply to ships length over 100 meter. Small ships normally, you see, we should understand this. They are interested sometime in the rules and regulations, the absolute dimension. You see, there is the port is 500 meter. Now, if the ship is small, say 50 meter boat, it is going to, even if it has a 5 or 6 times its turning radius, it will still be 300 meter, less than 500 meter. But bigger ships will be small, requiring more space. That is why the rules are more for bigger ships, 100 meter and all, mostly ocean going ships. Okay, you can apply that, and we have in fact recently checked it for a 60 meter vessel, but it is not a mandatory requirement. Then there are some kind of specification of what I should say, kind of
standard for ships length above 100.
Yeah. These IMO standards that we will mention here now are applicable for ships over 100 meter, and there are some other kind of ships, etc. And they should be done in what is called deep. The applicable conditions are for deep unrestricted water and in calm environment. For only fully loaded condition, and steady approach at test speed. Okay. Now I will tell. See, these are all standard. That means in a very standardized environment. Okay, in a deep water, ballast water condition, etc., a ship must possess at least so and so and so and so maneuvering characteristic. What are those so and so and so and so? This thing I will tell you. And this is to be done and checked finally by doing those maneuvering trials that we mentioned last class.
So steady approach at
test speed. Yeah, there is a now this there is a test speed given here, which should be that it is mentioned here. Test speed should be at least 90% of ship speed at corresponding to 85%, at least 85% of maximum power. I'll tell you the reason for that. You see what happened. You have a ship with a full power. Sometimes you don't actually, if you give the full power, you will have a higher speed. Say ship is designed for say 16 knot speed, but this standard, somebody will say that I am going to go at 14 knot speed always. But basically, it turns out that if you increase the speed, you normally have it has an effect on the turning abilities. So they specify that you must do this test at least at 85% of the maximum power, and at least at 95% of the the speed should be at least 90% of the ship corresponding to the 85% of power.
The 100% power, what is the speed? That 90%.
Yeah.
This is 85% of MCR.
Exactly.
MCR and what is that?
95% of the ship speed.
0.9 of that.
Yeah. Basically, it specifies a lower limit of speed. It must be at least at that speed. So you can calculate that. Suppose a ship is designed for 18 knots, the test should be done at least for the 16.5 knots, whatever. According to that, you cannot do it for 12 knots and say, because 12 knots it will basically so they have got this various rules and regulation. I am not mentioning that. They have got standard definition of what is meant by length, whether it is LBP or not, what is draft, how to be taken, all that are there in the rules. That is less important for me for this class so much. I want to concentrate more on the turning ability and the reason why they say that, rather than he will tell me that whether you take this L 100 meter is no, it should be 95 meter. That is the question of just reading the rule correctly.
In fact, all these rules, in the book, all the definitions are given in the beginning.
Yeah, it's here also. I am not, as I said, I am not reproducing the rules. I only want to just take all rules will have 3.21 to 1.22. This is a rules and regulation course. He will place it on your screen and you will read that.
We had all this.
Yeah, you had this. So I don't consider that that you can read it.
Yes.
I only want to stress here some of these final points, that is all. So, here that this condition are there. See, what it involves is turning ability. Three things it involves: turning ability, initial turning ability. Both of them you are testing through your turning circle maneuver and then zigzag maneuver. These two are main thing. This it says, now here I will just write this: advance, okay, should be less than or equal to 4.5 ship length, and tactical diameter should be less than 5 L. Now, if you see advance and tactical diameter, yesterday if you see that actually, if you go this way, I just write this diagram here, okay, where in fact here the advance has been defined to be where it is changed 90 degree, that is where you started turning. Advance is this distance. Advance was the distance along the x axis where the heading has just changed 90 degree, and tactical diameter was this where it is that another 90 degree here, and this. See, it is you may say, why not the maximum one? Okay, normally they are not doing the maximum one for I don't know what reason, because maybe it is much easier to measure the heading angle, locate this point more easily when the heading is just 90 degree, than to pinpoint the location of maximum width. So, and they seem to be close by. So, this should be less than equal to 5 L, and this should be less than equal to 4.5 L. So, it again is very important. Why these two parameter? Because you see, if there is a restricted water harbor there, you start to turn here, say some restricted water there, etc. So, obviously it will tell you how much of space you have got in front, how much you have got inside. See, the logic is very simple. It tells in this two how much you can actually have space front, therefore it must be less than that. That is why there is a specification with respect to the front distance, that is the advanced distance, and also the tactical diameter distance. Okay. In fact, it does not say here anything that I found out, maybe there is a question amendment about the turning radius actually. It tells about this too.
But sir, other way it is telling R by L only, that means.
Which is?
That R by L, what limit we have?
No, we don't have the limit. See, that's what I am saying. R by L, what I said, it is not the limit.
That is the normal thing happening.
Normal ships have R by L or D by L of that
So
much.
this way they have specified that.
IMO does, see, please, we have to understand this. IMO is more concerned about not making accidents. You don't turn or don't turn different, but you should not turn such large that you hit the other side. So it's a safety regulation. It is not trying to tell you that your ship is very highly maneuverable. It does not say that your ship is, the owner may not be happy, he will be happy. It is not going to hit the side. So these requirements are more of like that end, that prevention end rather than quality end of it. Okay. And the problem nowadays is that in the design's time, if it does not meet, then they will not sign it, and that's it. You see. So this is one of this thing. There are more details. The second thing is this initial turning ability. It says here, this also I did not say here. You may ask the question, what is the rudder angle given here? Okay.
What is that?
That rudder angle also they have actually specified here. The rudder angle should be, let me tell, something like, it should be the maximum rudder angle, which is 35 degree, but not less than some number. It should be actually basically maximum rudder angle. But there is some stipulation given on the rudder angle. Let me try to just find out this thing. Yeah, okay. It is basically 35 degree or the maximum rudder angle that is permissible. Normally most ships is 35 degree. Again 35, there is a reason which next lecture will tell you, because that's where the angle of stall occurs mostly. So that's why you have that way. But
we cannot have a radius smaller than this.
Yeah.
We'll have more than this only.
Normally so, you have more than this only. But this is anyhow, this is a stipulation that it says that
35 is specific. The radius it will make.
No. There is a point at which no force has started acting.
See, what happened is that we'll talk next class, hydrodynamics of rudder, that you keep on increasing more, you have plate here, you keep on making more and more and more, then it will not produce lift this side. It will not, it will like a plane. So there is a limit. In fact, no, it's like a plane. You know, if you want to go like that, it is not going to go up anymore because it is going to be just a drag. So for producing lift, you need an angle of attack. An angle of attack should be some. Yeah, normally they call angle of stall. After that, it actually comes down, and 35 also is very high. Most ships might be 30 degree. I don't know. You see, when you design it, you probably design up to 35 degree both sides.
But we don't go ever.
No, you don't go over. You don't need to go. You see, that's what I'm saying. Initial turning ability, because most of the ships, unless emergency, you don't make a U-turn to run away. See, for a big ships, that is because if you're a smuggler, you're being chased, you might try to run away. But they're small ships. But here you don't do it. You need to check that. But initial turning ability is more important actually. See, here it says that when you keep 10 degree rudder, okay, then this is interesting. It says the ship should, I'll tell you, just write it now, not have travelled more than L by the time see, it means that, see, the ship is here initially, okay, you give a rudder 10 degree. Now the ship heading will change. At some point the heading has changed to 10 degree. This distance must be less than 2.5 L. In other words, as it turns, as you know, this is a ship here. I mean, if you draw like that, here the heading psi is just 10 degree. Here psi is 0 degree. Rudder is being applied. You know, you are applying rudder. This is the starting point, whatever. What it says, it's called the initial turning ability. Initially, it should not be that you want to turn. It should not be that it is very slow to respond and it takes a long time and then begins to turn. You see, it can be. It should not be like this and then turn like that.
That limit is given.
Yeah. So okay, that limit is given. It should be turned more like this.
Should be full axle by 2.5.
Yes. By 2.5 length, by the time you reach the heading, must have begun at least 10 degree. The same rudder angle that again, it should turn 10 degree. In fact, these are all nice simulations are possible. As I told, I have got results of this full thing. We have done a simulation now for a design. See, these things are all requirements. Okay, how do you check the requirement? After you build the ship, IMO man will be there. The ship trial will be held, and you have to prove this. But to check that you know that these are the requirements. So at the initial stage of design only, you can actually kind of assess that by trying to estimate the hydrodynamic forces and try to do a simulation. Because if there you detect that the hull is really bad, it may not meet. You know, there's some chance. Of course, what you get there may not be exactly this, but you have a feel that it is bad. Then you should make an improvement right at the design stage in itself. So nowadays it is becoming, and many of the owners are insisting that when you do the design, along with the part of the design document should be the seakeeping behavior as well as the maneuvering behavior and the simulation showing the IMO satisfaction and criteria has been satisfied. I forgot to mention all these things will apply to both port and starboard rudder. Okay, now you may ask why port and starboard rudder. The thing is that as far as rudder is concerned, port and starboard makes a slight difference for a single screw rudder, because in a single screw rudder the propeller moves in one direction, so the flow that comes to rudder may not be exactly along the x-axis, slightly angled. So there is a bias one side and other. Many people will show you this simulation, you know, this will look like that and the other side will look slightly different. Not so much, but slightly different. They are not symmetric necessarily. So this rule applied for both sides. If it is because you know that the way it is that it is a ship here, there is a propeller here, rudder is here. This propeller is rotating in one direction. So the flow is having slight bias. It is maybe coming like that. See, propeller is rotating in one direction, so the flow is not symmetric exactly along the x-axis. No, how can it be symmetric? See, there is this is very difficult to draw a three-dimensional picture, but see, propeller is rotating here in this direction. So along this line, if you take a center plane, here, okay, See, if you take a center plane, I don't know how to show that, propeller is rotating one direction. So here the flow is not exactly along this line, it will be slightly having this side. You see, because propeller, had there been two side propeller, then it would have got counterbalanced. But it is one side propeller, you see. In fact, torpedo is so important that that you have a counter-rotating propeller, because you don't want any bias. That's why actually you sometimes you must be knowing that you have to give some zero rudder angle may not be the zero offset. You might have to give some small angle just to offset this.
So for a clockwise turning propeller, which one will take a bigger circle and which one will take?
That I cannot offhand tell, because I cannot offhand tell that this answer. Yeah, let me think that if you have clockwise turning circle, okay, that is this way and the ship is this side, then the flow tends to be actually biased this side. So angle of, it depends, you can make out from angle of attack. Most likely that the turn on
It will come on the port side.
on port side. I will tell you afterwards, but I tell you what you can do is that you can actually imagine that this is my rudder, so I am turning it this side, okay. Now the flow, if the propeller is right-handed side, there is a tendency of flow to move this way, so there is a vector will coming this side more. If this side more comes here, then this angle will be the zero setting angle more or less. That means you have to turn more this side. That means for port side you might have to turn more to get the same radius, and starboard side may be turned less. You can make it out from that. See, what would happen is that,
The thrust that is coming
yeah, no, what I am telling you, that because of this propeller, okay, let me
thrust on the rudder.
see, the propeller is moving in one direction, okay. So what happened, the flow direction will be average this side, not straight line.
Yeah.
So therefore, if the rudder is here, flow will be creating coming on this side, and in other words you can say that if you keep the rudder at this small angle, this will be the neutral angle. No turning force will come. Therefore, if you want to turn this side, I have to give more rudder here. So I end up giving, say, same angle from this place, which means more angle from the main line. See, this may be 28 degree, means 30 degrees from here. So the 30 degree may be equivalent to this side 26 degree. In other words, therefore, it means that if I give 30 degree here, it will turn quick. That means it will be smaller here, this will be larger here for the same angle. This is what I would think. I am only thinking from intuition, I have to check, but I think that is how you can make out. No, not thumb rule. It is also proven actually, rudder empirical formulas also tell you the rudder force is different in both sides, port and starboard.
Right screw propellers and right screw
Yeah.
left screw
So
propellers.
this logic, so when the propeller is moving, that water which comes out, it's not in the axis always. It will decide why actually.
But that is obvious, because something is moving in this plane. No, see, there is a flow here. Now, think of the point here. You are pushing it this side. Then naturally the flow is being pushed this side slightly.
Circular, it will come out.
Yeah.
Okay.
See, it is a circulation, so it has got an axial velocity this side and a velocity this side. See, any point is being pushed this side and this side, so they are vectored this way.
Resultant will.
Yeah, you see the fan here, our ceiling fan or any fan. You see the flow is in front, but if you take a vector, it is not exactly along the straight line. It will not be straight line, and this is why for a ship, if you have a twin screw, if you have this one this way, this one always this way, always have.
So that it balances.
Yeah, always.
So it's more stable. That's why.
Always. You cannot have in one side this way. That is always the case. See, the reason of one propeller, Professor Mishra might have explained to you, is that if you have one propeller, it is more efficient. Contrary to popular belief, more blade area, less RPM, one propeller is more efficient. So you have this ship propeller, big blade area, moving at not very high speed. You can even count 100 RPM. 1 a second like that.
On that rudder part, that angle is around 2 degrees.
Yeah,
Always
exactly.
it's offset.
Yeah, it is offset. That's why the reason is offset. Yeah, that's offset. It's
So
offset.
you resolve the forces, and one is giving
Yeah.
you the lift, and other is
Drag, yeah.
drag.
Now you have got, okay, now comes the zigzag. Actually, for zigzag, it is called yaw checking ability. See, these two that I mentioned, remember earlier, turning ability is both are output or results from turning circle maneuver. Yaw checking ability is basically coming from zigzag maneuver. It says here that for a 10-10 maneuver, I am again writing this the zigzag maneuver. See this 10-10 maneuver. the first overshoot angle should be less than 10 degree if L by V is less than 10 seconds. I will tell you about this one. Less than 20 degree if L by V is less than 30 second, and basically 5 plus some this is L by V by 2 degrees for L by V between 10 to 30. Forget this part. See what it says here. Now this is a stipulation about the first overshoot angle, and also it says the second overshoot angle. I will just explain to you this again in a very brief way. The same thing will happen for this. See what happens. See that there is an overshoot here. As you know, this is my overshoot. The overshoot angle is this angle. See, it is supposed to be 10 degree. At 10 degree heading your chart, so there is an overshoot. This is the first overshoot. The second one is more. Normally, second one is more. After only 2 or so, it stabilizes. That's why beyond 2 they don't go. This one is the second overshoot angle. Now this is given a stipulation with respect to 10 degree if L by V is less than 10 seconds. Now you may say why L by V? Now this is actually because it is found out that this overshoot obviously is connected to speed also. So if it is a higher speed, you expect a more overshoot angle. That is why they have given this L by V criteria. You see, if you think of a shape fixed L, V is increasing, then L by V is decreasing. Okay, when L by V decreases, then you must have smaller angle, lesser overshoot, because otherwise it tends to like heading is less, but the yaw angle will be more because it's less time to go up. So it kind of restricts the path width basically. So this is how they have given, because you want this overshoot angle. First of all, the criteria is with respect to first and second overshoot angle. Second of all, you wanted this overshoot angle to be somewhat connected to length and velocity. Longer ships should have be allowed more overshoot angle or whatever. This L by V parameter is there, and you can make out from there first overshoot will be 10 degree etc. And my saying is my emphasizing the point is that overshoot angle is obviously a criteria, but as overshoot angle depends on length as well as speed, the criteria has somewhat connected this with length and speed. L by V, you can see L by V is a unit of time, so L by V becomes actually like a time period, so it is tied with the time periods. This is how it is mentioned. See, let me say about this 2021, then I will, because we will have more time for that. For the same thing for 2020 maneuver, it says first overshoot should be less than equal to 25 degree. Something like that. See, again I will just, because we do not have so much time, I will just try to tell you the logic behind this. What they are trying to say is that 10-10 maneuver, which is more logical, normally you do not maneuver with a very high rudder angle. For 10-10 maneuver, the first overshoot and second overshoot angle are specified. Your ship must maintain that criteria. So first overshoot must be something, and that criteria is related to length and velocity. You can always work out by L by V etc. It is between 10 to 20 degree, and in between it is this formula is absolutely a straight line interpolation between the two. If it is less than 10 so much, more than 30 so much, and between 10 to 30 it is just a linear interpolation. Yes.
The first overshoot it should not exceed, or the second overshoot should not exceed the first overshoot.
Yeah. See, suppose first overshoot should not exceed. Now, by say here the answer is say the L by V is so that the answer is 12 degree. Suppose the L by V of a ship is such that the first overshoot should not exceed 12 degree. Then second overshoot should not exceed 27 degree. No, 27 degree. Second overshoot you will always find is large, and then actually all these ships you will find that it goes like that, then like that. I mean this larger here, then it stabilizes.
Plus 15.
Yeah, and now just to quickly say, because we have to very soon end, the same zigzag maneuver, another criteria is there for 20-20 maneuver, where the stipulation is only for first overshoot should not exceed 25 degree. Essentially, I want to tell you is that this is limiting the zigzag maneuvers ability for the ship to turn. So, it should turn, but here they are concerned about it should not turn, the overshoot angles are to be less, which means whether the ship turns or not, it should be safe. See here the IMO's requirement is not that it, supposing the ship turns very slowly like that, it is agreed to this thing, okay. It is agreeable to IMO. So, IMO is not bothered if your ship is really sluggish and turns very slow. They only want to make sure it does not turn so fast. Your enthusiasm, you have not given such a big rudder that it while turning it hits the bank on the side. That is what they are interested. And the last one is the stopping ability. I do not have so much time, but just to tell, there is a stipulation that the ship should stop within 15 ship length. That is all. The stopping ability is the final thing. This distance should be less than 15 L. Actually, but this can be changed, etc. But basically, if the ship starts here, it kind of stops here. Actually, it says that this distance, the actual distance, should be less than 15 L, where the V becomes 0. That is again a very important for tankers and all. But it says here the administration can change this because for many very large tanker, this may not work. So it can be.
Very long then.
Yeah. So. Yeah.
15 L is big.
Yeah. Okay, I mean I will end it here. Maybe we can pick up again little bit of that next class. So I will just stop here for the time. Now see.
This topic.
Okay. This hour we are going to speak about rudder. But I call this lecture as Rudder Hydrodynamics because we will concentrate more on this performance part of it, which is because of hydrodynamics. See, as you know, there are various kinds of rudder. I do not want to go into the detail. There are rudders which are like balanced, not balanced, having a post. Number of types of rudders are there. Okay, essentially rudder is a device which you can rotate about some axis, and by rotation it causes primarily force in the y direction. This is what you are interested. You want to generate turning moment and turning force. This is what exactly it is. So if you take a rudder here, something like that, it has got a rudder stock. It might have earlier as a rudder post, but as I said, I am not getting into the detail of the construction part of rudder. In fact, there used to be a empirical formula about the rudder area also, how much it should be. It turns out approximately 2% of the central plane area of the rudder, or some other formulas are there, like some empirical type formulas, d into L by 100, something like that. I will just give you one formula here, etc., etc. And this various kinds of formulas. It obviously it is dl by 100 gives you the percentage. That dl is the for a ship the center plane area, more or less this area. So 80 is some kind of percentage of that. As I say, if you work it out, this will turn out to be again around 1 or so, 2% or so. The purpose of today's now talk is that how rudder produces force, how the cross section look like, and some detail regarding its performance. Okay. So if you take a cross section of the rudder here, typical. See, this is a simple rudder. Actually, rudder will have many other shape. It can be triangular, it can be whatever. But if you take a cross section of the rudder here, invariably now this rudder will look like a aerofoil section, a symmetric aerofoil section. Okay. Let me draw from here. The rudder will be looking like I will just draw in this way. A turned rudder. It will have a symmetric aerofoil section. This is a typical cross section if you take, and I have assumed that it has been turned little bit. Okay, it will be turning about some point here. This may be the rudder stock point or spindle, I can call an axis about which it is turned. Okay. Now you have a force coming here, I mean the axis, let us say like this. So velocity comes this side, and I can call this to be angle of attack alpha. Let me again say, if you take a cross section of the rudder, see, first of all, why cross section for hydrodynamics? It is only obvious because you would expect the flow along the rudder to be along this line, not having a vertical motion much. So any cross section you take, you can find out, and you can take each cross section, add them up, you will get the total force more or less. So therefore cross section is very logical approximation, and I will just want to show or tell you what kind of forces etc. will be acting on that. You will have a rudder spindle here. Of course, this is a symmetric aerofoil section. Let us use the word hydrofoil. There is really not much. It is symmetric because, mostly because you want it to have same performance both sides, not like a airplane where you have an unsymmetric aerofoil, because you wanted the ship to only plane to only go up, not down. Okay. Similarly, propeller, you only want force in one direction mostly, therefore it is not symmetric. But in this case it is always symmetric because either turn port or starboard you want equal kind of forces. Now if you have a velocity coming here v, what happens is, as you all know, it is going to produce a force in some direction. Primarily there will be a component in this direction which is known as lift force, and there is a component in this direction which is called as drag force. Okay. There will be, therefore if I combine the two here, this is my net force, sorry, this will be my net force that will come. Okay. See, by definition in aerofoil there is a force there. You can call it this way, that the net force is this force, say F.